To use the one-to-one property of logarithms to solve logarithmic equations, we first express the equation in the form log base b of m equals log base b of n. This won't work without that. This form involves a single logarithm whose coefficient is 1 on each side of the equation. Second, we'll use the one-to-one property to rewrite the equation without logarithms. The one-to-one property says that if log base b of m equals log base b of n, then m equals n. That's what we're after. We will solve that resulting equation for the variable we're trying to determine, and then check our proposed solutions in the original equation. Include in the solution set only values for which m is greater than 0, that's this m, and n is greater than 0, based on the domain of our logarithmic equations, or logarithmic functions. Solve for x, and always check to make sure the solutions you get are in the domain of the function. Alright, on the left-hand side we have log base 3 of x plus log base 3 of the quantity x plus 1 equals log base 3 of 2. Now we can use our product rule on the right-hand side, because we have a sum of logs, to write the log base 3 of the quantity x parentheses x plus 1 close parentheses equals log base 3 of 2. Now, because this is in the right form, we have two logs with the same base, opposite sides. This means the arguments must be equal. So we can use this to say that x times x plus 1 must equal 2. Now, distributing the x on the left-hand side, we arrive at the equation x squared plus x equals 2. And then this is quadratic, so we'll want to subtract 2 from both sides. So we have the equation x squared plus x minus 2 equals 0. Now, my hope is that that factors. Let's see, so we could say x plus 2 and x minus 1. Yes, that'll work, okay. Which tells us that x equals minus 2 or positive 1, respectively, depending on the factor you look at. Well, because the original domain of each of these functions, log base 3 of x, tells us that x is greater than 0, and log base 3 of the quantity x plus 1 tells us that x must be greater than negative 1, the only valid solution we have is x equals 1. Must be greater than 0 and greater than negative 1. Our next example, solve for x. Always check to make sure the solutions you get are in the domain of the function. This one is natural logarithms, which have the same domain. So natural log of quantity 4x plus 6, close parentheses, minus natural log of parentheses x plus 5, close parentheses, equals natural log of x. We can use our quotient rule now because we have a difference, a subtraction of two logs. So this would be natural log of quantity. We have a fraction with our numerator being 4x plus 6 and our denominator being x plus 5, close parentheses. This equals natural log of x. Now, because the bases are the same, they're both base e, the arguments must be the same. So 4x plus 6 over x plus 5 must be equal to x. Now, this is a rational equation, so we can multiply both sides of the equation by x plus 5 to clear that denominator. That will result in 4x plus 6 equals x times x plus 5, which distributing that would be x squared plus 5x. This is a quadratic, so we want to get this equal to 0. So I'm going to subtract 4x from both sides and also subtract 6. So this becomes x squared plus x minus 6 equals 0. Now that factors. that factors as x plus 3 times x minus 2 equals 0, which tells us that x equals minus 3 or positive 2, respectively. Now, I should have examined my domain sooner, but 4x plus 6, we had natural log of 4x plus 6. For that to be greater than 0, that means that x is greater than negative 3 over 2. And for x plus 5, we had natural log of x plus 5. For that to be greater than 0, x must be greater than negative 5. Both of those have to be true for our solutions. So negative 3, x equals negative 3, is not greater than negative 3 over 2, so it is not a possible solution. However, x equals 2 is. So x equals 2 is our one valid solution to this equation.